timing things now. There we go. All right, so like I was saying, right, last time we learned about this idea of calculating the average value of a function, right? And we just use a little bit of calculus and apply it to stuff that we already know on how to calculate the average of numbers, right? If I was asking you just to ask you to find the average of a finite set of numbers, you would add up all those numbers and then divide by how many there are, right? And then we took it to the calculus level, and we were able to do this for infinitely many numbers between 2 points of a continuous function, right? So that's using the integral that allows us to take the sum of all of those values of that function that's between 2 points, a and b. And then we just divided by the distance it is from a to b, right? This 1 over b minus a. That's all that is, by the way. It's just how far away is a from b, and we divide by that. It's the same idea as dividing by the total numbers of how many numbers you have, right? That's all that is. And when you do this, this helps you calculate the average value of a function between those 2 points. So if we're looking at this function right here, 4 minus x squared, right, there's some positive values up here at x equals 0. There's some negative values over here at x equals 3. So if I were to add up all these values here, I'd get some number. And then if I were to divide by the distance from 0 to 3, I would get 1. That's what we found out. The average value was 1, right? And from this theorem, this average value of a function theorem, we also found out that there's got to be a specific value between a and b that the function is equal to it, the average value, right? It's called the mean value theorem of integrals. It's like the mean value of theorem that we learned for derivatives, except for derivatives, we were looking at slopes of tangent lines. For integrals, we're just looking at values, right? We're looking at the value of it, and that's all it is. So we did this example last time, right? We found the average value of 2x plus 3, right, on the interval from 1 to 5, okay? And we found out that the average value was 9, right? It was 9. And all this is saying is that what the mean value theorem of integrals is saying is that there should be some number that's between 1 and 5 where the function value itself should equal to 9. And that happens at 3. That happens at c is equal to 3, or x is equal to 3, we should say. So that's between 1 and 5, and that gives us that right there. Okay? That's it. That's the general idea of this thing. It's just to help you to find out where the average value is, where the x value is for the function to equal to that average value. Okay? All right. I know this sounds kind of crazy and weird, but that's the gist of it. That's the general idea of it. That allows you to do some of these problems to calculate the average of specific values of functions. Okay? So let's start off today. Let's do another problem just to get this practice ingrained here. Let's go ahead and start off with this one right here. Let's go with here. Let me zoom in a little bit here. Sorry, I'm late. Don't worry about Shine. You barely made it. All I did was just a review of what we did last time. So you didn't miss anything yet. We're going to go ahead and start off with the new problems today. So here we go. Let's go with this problem right here. Let's say I was given the velocity, right, of a particle. I can spell. Of a particle is given by v of t is equal to t plus 7. Find the average velocity for the first 5 seconds. For the first 5 seconds. For the first 5 seconds. All right, so taking a look at this, right? What do you guys think? What should we do? What's the average velocity going to equal to? Looking at what we've been looking at for this section so far, right? Is it any different from finding the average value of a function? Well, the velocity is given to you in a function. Do you see it right here? Right? It's a velocity function. So if I'm looking for the average velocity, I'm just looking for the average value of this velocity function. And to calculate the average of this function, right, we're just going to use that mean value theorem of integrals, aren't we? Right? To find the average velocity, that's just going to be 1 over b minus a times the integral from a to b. And, you know, it's f of x dx. But in this particular case, instead of f of x, we're going to use v of t dt. That's all that's going to be different from this problem. It's the same concept, right? So we just plug in those values. Now, here's the hard part. What are the values of a and b? That's the part that I'm going to have you guys kind of figure out. What is the value of a and b as I fill in the rest here? We got the t plus 7 dt, right? And Monica's going with 0 and 5, and so is Brian. Brian's going with 0 and 5. And what's the key word that lets you that led you to that answer of 0 and 5? That is correct. It's the first 5 seconds. We start at 0, right, and goes to 5. That's the first 5 seconds that you're going to be dealing with. So yes, that is correct. It's going to be 0 to 5 for your A and B, and that's pretty much it. Okay, that's pretty much it. Once you get to here, we just go ahead and do the integral and calculate the work that we get here. So when I have this one right here, this is going to be 1 over 5, and the integral of t plus 7. Remember, we talked about this, right? Using the fundamental theorem of calculus, we found out that the integral of a function is just finding the antiderivative of that said function, isn't it? All right, so the antiderivative of that said function is going to be, well, what is going to give me, if I took the derivative, is going to give me t. Anyone have any ideas? What's the function that when I take the derivative, I end up with just t? And Monica's saying it's going to be 1/2 t squared. I'm going to pause here for a little bit. I haven't got to check with you guys yet. Are you guys okay with finding these antiderivatives? Does anyone have any questions about where this came from? How are those connected, right? Brian's got it and Monica's got it. That is the right answer. Oh, I just saw it. Monica put x squared. It is supposed to be t squared. We got to make sure we mind our t's and our x's. But that's not the main thing I wanted to point out. Like, does everyone feel comfortable with where that's coming from? It takes a little bit of getting used to looking for the antiderivative of things, because we've been doing derivatives for so long. I just kind of realized I rushed through this for the first week or so that we've been learning this. I kind of just like assume that you guys knew how to go backwards with your derivatives. Are you guys okay with it? Does it make sense where this 1/2 t squared comes from? And if not, you know, this would be the time to ask, because I'm going to keep going. I'm just assuming that you know. Maybe you do. Maybe you do. Maybe you do. I don't actually know, but I think you do. All right, right here for the plus 7, that's going to be plus 7t, right? Plus 7t, because again, if you take the derivative of 7t, we end up back at 7. That's the idea there. You know what? I'm just going to write it off on the side note right here, just in case. Some of you guys do have that question, but you don't want to ask because you're shy. Right, but for this side note right here, note that if I took the derivative with respect to t of 1/2 t squared, that would just equal to t. And same thing if I took the derivative with respect to t of 7t, that would equal to 7, right? And that's where those guys come into play. That's where I got this and this, or that's where Monica and Brian got those values for the antiderivatives. All right. This, of course, is being evaluated from 0 to 5. And I got asked this in my last period, 4th period yesterday. You guys also okay with this right here? This line right here? This, there's no real, actually, I've asked other people. They say they call it, a couple of the teachers call it the evaluation line. It's what you're evaluating your function from and to. I don't think they have a specific name for it. But that's all that line is, by the way. That's just telling you, hey, evaluate this function at 5 and then subtract this function evaluated at 0. Okay? So what this will look like is right here. So I'm going to have the 1/2 and 1 over 5 in front, and inside here, right, I'm going to be evaluating the 5 and the 0 for this function in here. So I'm going to have here 1/2 5 squared plus 7 times 5, right? That's the first part of it. And then I'm going to be subtracting this from 1/2 times 0 squared plus 7 times 0. See, that's all that line is telling me to do. It's telling me to take this entire function right here, take this entire function, and evaluate it here at 5 and here at 0. And then subtract the 2. That, by the way, is called the fundamental theorem of calculus part 2. I didn't actually tell you guys this, but that's what it is when you're doing these integrals. They have the fundamental theorem of calculus part 1, which was that connection that we made. The derivative and the integral are inverse functions of each other. And the fundamental theorem of calculus part 2 is this guy right here. I had you guys write this down earlier, right? If capital F of X, wait. Oh yeah, it had something like this. I believe, I'm trying to remember here. How did I teach it to you guys? I told you guys, right, if I take the derivative of this capital F of X, it's going to be equal to little f of X, right? And we say that F of X is the antiderivative of F of X, right? That's not the second part of the fundamental theorem of calculus. The second part is this, right? And then if I take the integral from a to b of F of X dx, that's just going to equal to the antiderivative evaluated at b minus the antiderivative evaluated at a, right? But in our shorthand or shortcut, or when you look at it in books and notes, what they tend to write out instead before this part, they like to write it out as the antiderivative, right, evaluated from a to b, like that. That's what that symbol represents, by the way, just for those of you who had that wonder of like, why the heck does Knockme keep writing that line? It's just a shorthand for this. And I know some people are just like, why don't I just go to this line? And it's just a habit that I can't break. I'll be honest with you. That's just what I've gotten used to. Anyways, I've gone on a long-winded side note here just for doing this simple problem here. All right, here we just go ahead and evaluate this all the way through. This is going to be 1/5. Right over here, I'm going to have here 5 squared is 25 over 2 plus 7 times 5, which is going to be 35. This whole thing is going to go to 0, right? 0, 0, minus 0. So that's going to go away. So I just have to add these two together and divide by 5. And I think if I were to do that, let's plug this into my calculator. I'm too lazy this morning to do this calculation. Maybe some of you guys already have it when I was rambling there. 25 divided by 2. Knock me. All right, let's just try this again. 25 divided by 2. Right, plus 35, right, is that, divide that by 5. And that's going to give me 9.5. So the average velocity of this thing for the first 5 seconds is 9.5, is 9.5. And that's it. That's your answer. It doesn't ask me where this occurs, or when, I should say, not where. It doesn't ask me when does this occur. We could find out when this occurs, right? We can just go ahead and solve this by setting it equal to the velocity function and finding out when does the velocity function equal to 9.5. And you can see that at some point between 0 and 5, there should be a time t where the velocity would equal to 9.5. And that's an easy problem to do. But that's the general gist of it if you're looking to calculate the average velocity given the velocity function. Now this is the part that's interesting. Well, maybe not interesting to you, but I find interesting. Let's say I was given a position function. I was given a position function. Oh, were you guys able to copy this, by the way? Can I move on? Can I scroll away from here? Are you guys good? Give me a yes or no. If I can move on. Yeah, Monica's saying yes. Everyone else got it? All right. So this right here seems simple enough, right? Thank you, guys. I appreciate you typing in the chat. This seems simple enough, right? You're like, okay, I just have to remember if I'm calculating the average velocity, I just do this right here, which is 1 over b minus a times the integral from a to b of the velocity function. And that's so lengthy to say. But here's the part that gets confusing now. Remember, position, velocity, acceleration, all are related to each other, right? If I give you a position function, you could find the velocity function. If I give you the velocity function, you could find the acceleration function, right? So here's the part that gets tricky when they start mixing these problems together. They're not going to tell you, what to do on the AP Calculus exam. That's the hardest part. You have to figure out what to do, and you have to use these little bits of knowledge that you've gained over the past semester and a half, right? So check this out. This is the part that I find a little interesting. Let's say I was given instead, right, the position function s of t is equal to, you ready? 1/2 t squared plus 7t. Right? Given the position function right here is equal to this. Okay? And I asked instead to find the average velocity for the first 5 seconds. I just say this looks very similar to the last problem. I could just apply the average velocity, the average value of a function again. The value, your answer is going to come out the same, Monica, but it's not going to be done the same way. If I asked you this, to find the average velocity for this position function, this is the part that I'm going to tell you right now. A common mistake, once students learn how to calculate the average value of a function, they'll immediately go into this, the average value, they'll immediately go into this equation, 1 over b minus a times the integral from a to b of f of x dx. Every student does it. As soon as they see the word average, this is one thing that they'll try to jump into. But that's not the case in this problem, because I don't have the velocity function in this case. Now, there's 2 ways we can do this. There's 2 ways we can do this. We can find the velocity function, can't we? Because if I know the position function, which is 1/2 t squared minus 7 plus 7t, right? I can find the velocity function by taking the derivative, right? If I take the derivative of this whole thing, the velocity function is just equal to t plus 7. And then I can go ahead and take this and plug it into that, and we would get the same answer. But we've already learned how to calculate the average velocity if I'm given a position function. Do you remember how to do it? We called it the average rate of change. Do you remember how to find the average rate of change given the position? Brian is right. Position divided by time. Right? Check this out. If I was looking for the average rate of change, right, from 0 to 5, why, that's just going to be this guy right here, isn't it? It's the slope from the end point minus the beginning point. So the average rate of change, right, is just equal to s of 5 minus s of 0 over 5 minus 0. Huh. Wasn't that weird? That, well, s of 5 is just this guy right here, isn't it? Here's my s function right here, right? So s of 5 is telling me to go ahead and calculate 1 over 2 times 5 squared plus 7 times 5, right? That's the 5 part. We're going to go ahead and subtract that from the 0 part, which is going to be 1 over 2 times 0 squared plus 7 times 0. isn't it? All over 5 minus 0. Well, if we do all this, this up here is going to give me 25 squared, or 25. 5 squared is 25 over 2 plus 35 minus, that just goes off to 0, right? Divided by 5. And that's the exact same thing that we were doing up here, isn't it? But we didn't have the position function, did we? We had the velocity function, and we used this average velocity, or I'm sorry, average value equation to help us find it. Isn't it crazy that it connects to the same thing if I was given the position function? It's kind of, I don't know, I think it's kind of interesting, but maybe you guys don't see it the same way, but or maybe you do. Hopefully you do. I can calculate the same thing without having to do the derivative and then go ahead in there and doing the integral, right? And you'll say, knock me, we've done that before in the past. Why is that such a big deal? Well, now, in case I don't have the position function and I have the velocity function, I have a way of going backwards now. I have a way of calculating things that I wasn't able to before. Anyways, that's the idea there. That's the application of the average value function. And now we can go backwards and find the average value of a particular function instead of just going with the derivatives to find the average rate of change of a function, right? Anyways, I've gone on a long-winded speech about that, but hopefully you guys are okay with that. That's not too bad, right? You guys okay? Not okay? You're slightly confused as to what the heck am I talking about? Let me give you a problem. Let me ask you guys to do one problem for me. Okay, let's go with that. All right. So let's say I have here, for example, right? Let's go with given f of x is equal to 3x squared plus 7. Okay, 3x squared plus 7. Find the average value from, here we go, let's go with 0 to 2. 0 to 2. All right, I'm going to ask you guys to try this right now. I'm going to set up a I'm going to set up a pear deck for this one. Can you guys go ahead and try this one for yourselves? And I'm going to ask you guys to give me the answer on a pear deck. So I'm going to give you guys that chance right now. So I'm going to go set up a pear deck real quick. Real fast. Let's do this real quick. So just try this out. Just do it on your paper. You don't have to show me the work on the pear deck. I'm just going to ask you to give me your answer. But if you don't have an answer, right? This is just a function, f of x, not a velocity or anything. So this is asking, oh, that word at the end, that's value. My writing is kind of messy. The average value. The average value. Sorry. All right, so let's go ahead here. AP Calc, AB, mean value theorem for integrals. There we go. Delete. And add on pear deck. And we'll do this right here. Is that drawable? And yeah, give this one a try. Give this one a try. Ignore that gigantic 5 up there. Why is that 5 there? There we go. Excuse me. Keep yawning. That's rude. Okay, so here's the pear deck. You guys can go in here, joinpd.com, the AKFNS. So you guys can go in there and give me your answer. But if you're uncomfortable or unsure of your answer, you can also write down what it is that you've plugged in just to see. You can just see how much partial credit you would earn. Okay. So it's a blank canvas on there. You guys can go ahead and go on there and just give me your answer, give me your work. See what it is that you got. Juliet, that probably isn't your answer, but that's a nice it's a nice drawing you got there. Yeah. So I just want to make sure you understand. All right, you guys see that when you do the average value theorem, you gotta be careful on the wording of it. All right. Let's see how you guys are doing. Excuse me. Let's see. David just straight up got the answer. All right. Brian, that looks good. That looks good. What you have there so far is good. Juliet, that's a great start. Monica, beautiful setup, and then it looks like you got your answer there. Oh man, you guys are killing it on this one. Good, good. Keep going, guys. Keep going. I'll come back in about a minute or so. All right. So the setup that you guys hopefully would have gotten, right? If you're looking for the average value of a function, right? The average value of f of x, right, needs to be equal to the 1 over 2 minus 0 of the integral from 0 to 2 of 3x squared plus 7 dx, right? If you got there, right, and they're asking for the average value, you would get a point, at least a point for that, for setting it up correctly. So if you can at least get there, you're good, at least on the starting part, at least setting it up. That's the hard part, I'm telling you. And again, it's not gonna be as straightforward as here's the function, find the average value of that function. But you know, you got to start somewhere. Now, once you get to here, right? We practice this out here. If you're going to evaluate this thing, 1 over 2, The integral, remember the fundamental theorem of calculus is telling us to look for the antiderivative of this function in here, okay? So the antiderivative of 3x squared, I'm hoping you guys can see, is just x cubed, right? It's just x cubed. And again, if you're having trouble seeing that, if you're having trouble seeing why does 3x squared become x cubed, right? The question that I'm asking is, what, when I take the derivative of it, is going to equal to 3x squared? And x cubed is that one, right? If I take the derivative of x cubed, that's going to give me 3x squared. That's where this comes into play, okay? Plus 7x, same thing. I'm asking myself, what, when I take the derivative with respect to x, is going to give me 7 by itself, and that's just 7x. The derivative of 7x is 7. So 7x is the antiderivative of 7. This, of course, is going to be evaluated from 0 to 2. And then from here, we just have to plug in the values that we have for x. And I should get right here, this is going to be 1/2, right? 1/2 times 2 cubed plus 7 times 2 minus 0 cubed plus 7 times 0. You notice I like putting brackets around my parentheses just to make it easier to see the parentheses. You don't have to do this. This is just a habit that I've gotten into, and maybe you guys, if you guys see it enough, you guys realize that brackets, parentheses, they mean the same thing. It just makes it easier on the eyes. Okay, evaluating this out, I have here 1/2. 2 cubed is going to give me 8 plus 7 squared is going to give me 14. 0 and 0 is going to cancel out to 0. So I have over here 8 plus 14, which is going to give me 22. Half of 22, the average value is 11. The average value is 11. So that's to calculate the average value, right? All right. Good job for those of you guys who shared on here. I see the answer that you got there. So some of you guys might have gotten a different value. You might want to double check what happened, what went wrong. What did you do differently? What is something that you can see yourself, you know, what was the easy mistake that you can catch and try to fix when you're doing this problem? All right. Once you got that, how good is your algebra skills? How good is your algebra skills? With this being done, can I ask you guys to find C in the interval from 0 to 2 such that f of C is equal to the average value. So this right here, this question that I'm asking right here, this is the mean value theorem for integrals. So can you help me find out what should C equal to so that it's going to equal, so the f of x is going to equal to 11, right? The mean value theorem for integrals says this. By the way, this only works if the function that you're dealing with is continuous, which most of the times when you're dealing with integrals, they're going to be continuous functions anyways. Most of the times, if you're doing them by hand. All right, so the mean value theorem for integrals states that there should be a value where f of x is equal to 11, right? Well, what was f of x? F of x was 3x squared plus 7. 3x squared plus 7 is equal to 11. How did I solve this? What did I do? Do you guys remember how to solve quadratics? Do you guys remember how to solve things that have x squares in them? And Monica's like, yes, of course. You got a couple ways of doing this. What's the strategy that you would do for this problem? How would you attack this? What's something we could do? Subtracting the 7. I like it. I like it. This one was easy enough, right? It didn't have like an x squared and an x. So we don't have to do this by factoring or using the quadratic formula. We could just isolate the x squared term, right? Or maybe I gave away too much. Subtract the 7 from both sides. I end up with 3x squared is equal to 4. Divide both sides by 3. I have x squared is equal to 4 over 3. What now, guys? What now? Oh, guys. What now, everyone? No, that doesn't sound good. What now, people? No. Square root both sides. That's right. So x is equal to plus or minus the square root of 4 over 3. Which one is in the interval from 0 to 2? Which one is in the interval from 0 to 2? And Monica is saying the positive value, right? The positive value. And you double check that, by the way. Is the square root of 4 over 3 in the interval from 0 to 2? Don't just, don't be lazy about it. Double check it if you can. 1.15, and that is between 0 to 2. So in this particular case, c is equal to positive the square root of 4 over 3. Or if you guys don't mind, I'm going to write it as 2 over the square root of 3. And that would be it. That's the mean value theorem in a nutshell. And the mean value theorem comes from finding the average value of a function. And yeah, so just like in the past, the mean value theorem for derivatives, the main thing was to prove that that point exists. For it in integrals, it's the same thing. But again, when they apply these ones, it's most of the times they're applying to check to see your algebra skills. Can you still solve these things? And if it's on a calculator section, you don't have to do it by hand. You could just graph it and solve and see where does it equal to that. Because honestly, sometimes the functions they give you for these ones, they get ugly. They get ugly. They get ugly quick. And solving quadratics is okay. Solving cubics gets questionable for some. And then if it, if the function just comes out looking kind of crazy or weird, we would just use the calculator to solve it. See when does it cross that value. Okay. All right. Okay. That's it for the mean value theorem and the average value of a function, right? Not too bad, not too hard, right? Not too messy to deal with. What I wanted to do today was go back to these guys right here. We learned these earlier. We learned the fundamental theorem of calculus part 1. Right, so I wanted to bring this back up. And we also learned the fundamental theorem of calculus part 2. I don't know if I told you that we learned part 2, but we did. we've just been using it without saying that it's the fundamental theorem of calculus part 2. But here, let's go ahead and break these two down. Okay, the fundamental theorem of calculus part 2, let's do that one first, right? The fundamental theorem of calculus part 2 states this, right? If f is continuous on a to b, right? And capital F prime of x is equal to little f of x, meaning capital F of x is the antiderivative of f of x, then, right, the integral from a to b of f of x dx can be found simply by using the antiderivative evaluated at b minus the antiderivative evaluated at a. This is the second part of the fundamental theorem of calculus, and we've been using this like for a good amount of time now that we've learned about integrals, right? And that's all fair game. And again, this came from the idea from the first part of the fundamental theorem of calculus. The first part of the fundamental theorem of calculus was this idea, right? We went through that whole long thing with that worksheet, and we found out that f of x, the integral and the derivative are basically inverse operations, right? They're inverse functions of each other, okay? But if you want to write it down, this is the idea here. If f is a continuous function on a to b, then the integral function capital F defined by, let's take it like this here, f of x is equal to the integral from a to b, a to x of f of, give me a, I'm gonna put in a dummy variable here, so don't get thrown off by this right here. F of, let's say, s ds. Just a side note, s is a dummy variable. By the way, dummy just means that it's a placeholder. That s is just a placeholder. Normally we put x's in there, but I have the x right here as part of my integral, so I'm going to put it up there. Right? If this f, capital F of is defined by this integral function right here, right, and is this right here, if this is continuous, on a to b and differentiable on a to b. I know this is a lot of things here. Then f prime of x is equal to f of x. I'm sorry, this is so wordy, but this is the idea right here. I take the derivative of that integral function, I end up back at just the function inside here, but evaluate it at the x that's up there, or whatever values that are there. You guys okay? I'm always like that's why we did that whole lesson on it. Like, just if I just gave you this definition at the start, it's kind of like, what the heck is all of this? But remember, we went through all that work just to realize, right? The idea is this, right? What we use them. Oh, I should leave that there so you guys can get this down. But what we use the most is the idea that if I were to take the derivative of the integral, I end up back at the function that was inside that integral function, right? And it's the idea that differentiation and integration are inverses of each other, right? That was the main goal from that. That was the main pull from that. And this is just what they actually write down in books. This is the definition they use in there. And it's just a fancy way of saying what I just said. Differentiation and integration are inverses of each other. That's the main thing, right? They cancel each other out. The integration function is the antiderivative, right? So why am I bringing this back up? We've already been using this so much. We've been practicing this so much. Why am I bringing this back up? What the AP exam likes to do for the, so in calculus, I'd say the more important part is the part 2. That's what we use to actually evaluate the different integrals, right? The fundamental theorem of calculus part 2, I'd say is more important, but that's a poor way to think of it. I like thinking of it that way. But the AP exam loves putting problems that use the fundamental theorem of calculus part 1 just to see how well you understand the fundamental theorem of calculus. And let me show you what I mean. So, for example, right? Where is my examples actually? Here we go. There you are. You're over there. Let's put you over here. Okay. Close you. There we go. Okay. So here's the thing, right? They'll give you a problem like this most of the times. They'll give you a problem like this. They'll say, let me see here. I had some examples that I wanted to show. This will do. So they'll have something like this. They'll say, what is the derivative of the integral from a to x of f of t dt? So they'll give you something like this, right? They'll give you something like this. Now, if you know the fundamental theorem of calculus part 1, you would know that the answer is just going to be f of x. It's just going to be f of x, right? And you can do this multiple times and you'll actually come through and you'll realize it works out just like this. But let me show you why that is the case, okay? First things first, let's let f prime of x be equal to little f of x. Let's let capital F be equal to the antiderivative of f. Okay. So when I do this integral right here, right, from a to x, right here, right, I'm going to get, you ready for this? The antiderivative of f of t, which is going to be f, but yeah, it'll be f of t, right? But this is, of course, going to be evaluated from a to x. Okay, that's what I have so far. Now, when I evaluate this, right, remember this evaluation line right here, this guy right here, is telling me to plug in the values of x and then minus it from the values of a. So this right here is going to be giving me capital F of x minus capital F of a. And I need to go ahead and take the derivative of that, right? Now check this out. Check this out. The derivative of f of x, of capital F of x, right? The derivative of capital F of x right here, right? That's what this is showing me, right? That's what ddx of f of x is, right? That's this guy right here. That we found out that this right here is just going to give me f of x. The derivative of f of a, remember, a is a constant. A is a constant. Keep that in mind. A is a number. If I take a derivative of a number, what do I always get? What do I always get? What's the derivative of a number? Does anybody know? Just a coefficient, just a constant. Yeah, the derivative of a constant is equal to 0. So f of a, right there, that just goes off to 0. And that's why this right here, when I take the derivative with respect to x of the integral going from some number to x, it doesn't even matter. That's the thing. This a could be equal to 0. This a could be equal to 5 billion. It doesn't matter, whatever that number is. It's still just basically plugging in x into that function, right? We end up back here at f of x. So that's what the fundamental theorem of calculus part 1 looks like in a nutshell. So let me show you a problem here. If I was asked to find here, find the derivative of the integral from 0 to x of 2t dt, of 2t dt. You don't actually have to do this work. You don't actually have to go through the process of doing this integral, evaluating it from 0 to x, and then taking the derivative of it. The fundamental theorem of calculus basically states this. This right here is going to be equal to, you ready for this? 2x. That's not an x, knock me. How can you say x and then write t? This right here is just going to equal to 2x. And this will happen every single time, right? I can show you the work for this, by the way. d dx, right, of the integral, and I'm going to do this integral right here. This is going to be 2t, the antiderivative of 2t is t squared, right? And I'm going to evaluate this from 0 to x. Well, when I evaluate this is going to be the derivative with respect to x of x squared minus 0 squared. Okay? But when I take the derivative of x squared, I get 2x. And when I take the derivative of 0, I get 0. So what I'm trying to tell you is you don't need to do all of this work if you know the fundamental theorem of calculus, which is the derivative and the integral cancel each other out. And you could do this for crazy looking functions. It doesn't necessarily have to stop there. It could be something ridiculous looking. You ready for this? You ready for this? You're not ready for this. Give me a second. I'll give you a second because I don't know if you wrote this all down or not. But if you have, check this out. If I was taking the derivative of an integral function that goes from 2 to x of the square root of 2 plus cosine of t dt, I don't know what the antiderivative of the square root of 2 plus cosine of t is. I don't know what that is. But my point is this, I don't need to know what that is. Because right after I take the integral of it, I'm going to be taking the derivative of it, which means I'm going to end up back at the function I'm looking at. So I don't need to know what the antiderivative of this thing is. That's all I'm trying to say. So if I were to actually ask to evaluate this, you know what this is going to equal to? Some of you guys might have already guessed it. I don't care, by the way, that this is a 2 and not a 0, because again, if I take the derivative of something that evaluated at 2, that's just going to equal to 0. But check this out. This is the part that's neat. The function inside is just going to be equal to that self if I take the derivative and the integral. So this is going to be the square root of 2 plus cosine. But here's the kicker, though. What's the variable I'm going to write in there instead of t? x. That's it. That's it. Ta-da! That's what the fundamental theorem of calculus is basically asking you to do. So if they give you something crazy, right, that's all you have to do. It's not too bad, right? They say there's got to be a catch to this, and there is. There's always a catch. Always a catch. Always a catch. Just a little bit. Just a little bit. So you ready to see the catch? When you do this right here, right, this derivative of an integral, they are, like I said, inverses of each other, and they do technically cancel each other out. But when you do derivatives of things, chain rule, product rule, quotient rule, all those rules, they kind of go out the window when we're doing it with the integral, because the integral and the derivative, like I said, they cancel each other out. What doesn't actually work completely as well as this is if I were to do this fundamental theorem of calculus with the chain rule. The chain rule doesn't apply as cleanly as this, right? Because I have to take this function, I have to plug it into here, right? And then I have to take the derivative of it to get back to this function. What am I saying? So this guy right here, right? This is 2t. I end up with t squared. I have to plug in that x value, and then I take the derivative of that with respect to x. I just end up back here at 2t, but with it evaluated at x. If the integral doesn't have just x by itself, but it has x squared, let's say. So let's say, let's do one quick problem real quick here. Let's say I have here d dx, the integral from let's say 5 to x of knocking. Why are you drawing a blank on this? 3x squared. Nope. 3t squared dt. Right? 3t squared dt. Okay. If I was doing this problem right here, right? Again, just knowing the fundamental theorem of calculus, this is going to come out to be 3x squared. Right? That's it. That's it. That's all it is going to equal to. And again, I could show the work, right, by doing the actual thing here, by doing the antiderivative of this. Antiderivative of 3t squared is going to give me t cubed evaluated from 0 to x, right? Of course, when you evaluate it, I'm looking to take the derivative, right, of x cubed minus 0 cubed. When I do this derivative, 0 cubed just goes away. The derivative of x cubed gets me that 3x squared. Right, that's nothing new. But if you were to do this using the chain rule, if I looked at this exact same problem, I'm asking you to take the derivative with respect to x of the integral of 3t squared dt, right? The integral and the dx should cancel. But check this out. If I plugged in instead of x, I plugged in x squared. If I plugged in x squared, this is the part that gets a little tricky. A little tricky. You ready? Watch this. Let's do this by hand before I show you the shortcut. If I do this by hand, right, d dx, the antiderivative of 3t squared is still t cubed. And this is going to be evaluated from 5 to x squared. Right? Now, you ready for this? This is the part that gets a little funky. d dx, right, is going to equal to x squared cubed minus 5 cubed. Now, when I take this derivative, right? When I take this derivative right here, you got two ways of doing this, but I just want to show you this way first of all. This is a function inside of a function. And when you take the derivative of a function inside of the function, you need this thing called the chain rule. You remember that? The chain rule. So when I take the derivative of this, the derivative of x squared is 2x, right? My in function is x squared. So the derivative of x squared is 2x. My outer function is some stuff cubed, right? The derivative of some stuff cubed, right, is 3 times that said stuff. right? 3 times that said stuff, so which is x squared squared. I know this looks messy. So if I clean this up, 2 times 3 is going to give me 6. This is going to be x to the 4th times x. This will be x to the 5th. Right? I'm not going to write it like that, though, but this one kind of looks cleaned up here. But if you look up here, right? If you look up here, if I bring this up here, this is what I get when I take the derivative. By the way, the derivative of 5 cubed, that's just going to be 0. So, plus 0. So I'm not even going to include that right there. But here it is. The answer for this one right here is not just 3x squared squared, which, by the way, looks like that should be the case because I'm plugging this into where t is right there. You see that? Just like I've done over here, this x right here gets plugged into this t. That's why I get 3x squared. It looks very similar to it, doesn't it? But there's another factor that I have in front of it. Do you guys see that other factor that I have in front? That other factor that I have in front is 2x. What do you notice about the 2x? What can somebody tell me? What's the connection with that 2x that we have there? What do you think that is? That's has a relationship with the integral right there. Not the antiderivative, but it is of b, but it's not the antiderivative of b, it's the derivative of b, right? It's the derivative of b. We're taking the derivative of what's there in b and multiplying to it because of what? Because of the chain rule. So if I have something that's not just a, and we actually do this over here. What's the derivative of x? The derivative of x is just 1. You know that? And we actually put that there. We just, I mean, technically, I was supposed to teach you that first, but we kind of just went with a shortcut for when it's just x in the integral, right? But now that I show you that those functions are not just x's by themselves, we need to chain rule that thing and multiply it with the derivative of the antiderivative. So you still get this, by the way. You still get whatever the function is, evaluated at what b is, right? But now you also have to remember to take the derivative of that integrand that's in there. Because if you don't, you miss out on the point that you need there, the chain rule that you need there. So the chain rule does apply to this thing. So you got to make sure you do that when you do these integrals, right? When you do these fundamental theorem of calculus problems. So let me show you another problem. And you're going to start realizing like, wow, this is actually a little bit easier than having to deal with antiderivatives of things. And the application of it is easier, but the concept, the idea of it is a little bit hard to grasp, right? So let me show you another problem. So let's take a look at this one right here. So let's say I was asked to take the derivative of the integral of 3 to the x squared of the square root of 5 plus t cubed dt. If I was asked to do this, again, I don't know what the antiderivative of 5 plus t cubed is. No idea, no clue. And I can't plug this into my calculator because if I plug in this with x squared in there, it doesn't know to, do it. It tries to evaluate it. It tries to give you a number. And it actually does. It actually will give you a number. And that's not the answer that you have there because we don't have the x value. X is supposed to be this infinite variable that can be any number. So if I were to try to do this by hand, I have no clue what the heck the antiderivative of this is. Like no clue. None. Nada. Don't know how to antiderivative that. Yeah, I'm not even lying. I'm trying to figure out, can I do this? And I can't. But I do know this. I don't really care because I'm going to be taking the derivative of it right after that. So I should, in theory, just end up back at the function I'm dealing with. I should end up back at the square root. That's a ridiculously large square root. The square root of 5 plus something cubed. That's where I should end up back at. What's that something? That something is going to be x squared. So I'm going to write that in there, x squared. That's what the fundamental theorem of calculus is telling me. The integral and the derivative is going to cancel each other out, and we just evaluate it at the integrands of the values that we have in there. But I'm not done, though. I'm not done, because this also needs to multiply with the derivative of x squared. We have to chain rule this because of the derivative. right, of that. And when we take the derivative of that x squared, the chain rule tells me that the derivative of x squared is 2x. And all you need to do is multiply it with the derivative of the outside function. Basically, if you're thinking about it, this whole thing is considered the outside function. This whole thing is considered the inside function. And if you remember the chain rule, you just multiply the derivative of the inside times the derivative of the outside. And you get that. Is that okay? Does that kind of make sense? Or are you kind of like, what the heck are you talking about? Wait, that's it? Yeah, that's it. That's it. Kind of, yes. It's a little strange. I'm just letting you know, it is a little weird. But let me show you another one. I know it's like, oh God, you should show me another one. But let me show you another one. Let me show you another one. Let me show you another one. And I think you'll get it after this one. I'm going to write it a little bit differently this time, okay? I'm going to write it a little bit differently. So let's say I have here d dx of the integral from 1 to x cubed of the inverse tangent of t dt. Again, I have no clue what the antiderivative of the inverse tangent is. I know the derivative of inverse tangent. I have no idea what the antiderivative of the inverse tangent is. So to solve this, let me show you this way instead. Let capital F of x be the antiderivative of inverse tangent of x. Okay? So I'm going to use a substitution method here. I'm going to say that I can evaluate this right here, right? But using capital F of x. Okay? So what I'm saying is this integral right here is going to be equal to capital F of x squared minus capital F of 1. I don't know what the antiderivative is. I'm just going to let f equal to it. Okay? And now that I let f equal to it, I'm now going to take the derivative of this. I'm going to take the derivative of this. You ready for this? The derivative of this, right, is going to give me this right here. I have to chain rule this guy right here. This is going to need the chain rule. And when I chain rule this, hi dog, you just opened the door. You coming in or not? Okay. My dog just opened my door and is not coming in. Sorry, distracted. So chain ruling this, the derivative of x squared, right, is 2x. The derivative of f, right, capital F, right, f prime of what I have in here is x squared, right? And over here, that derivative of this is going to be just equal to 0. But here's the part that's the kicker. If capital F is the antiderivative, capital F prime, right, is the derivative of that. Well, what's the derivative of this? Derivative of this is just inverse tangent. So I can rewrite this out. This is going to be equal to 2x times the inverse tangent of what's inside there? X squared. And that's it. Wait, why did I write x squared? Hold up. Did no one catch this? Did I make a mistake here? I made a mistake here. You guys catch my mistake? What was this supposed to be on the inside function? It's not supposed to be x squared. It's supposed to be x what? X cubed. You guys just let me make that mistake this whole time? That should be cubed. Cubed. And the chain rule is also wrong then. Right? That should not be 2x. What should that be in front? What's the derivative of x cubed? What's the derivative of x cubed? That should be 3x squared. Yeah, so that should be in front here, 3x squared times 3x squared. There we go. And that's going to be the answer for this guy right here. This is what I'm saying. If I take the derivative of the integral from 1 to x to the third of the inverse tangent of t dt, I'm saying that this whole thing is equal to 3x squared times inverse tangent of x cubed. And that right there is your answer. You guys okay with this fundamental theorem of calculus? Part 1. Yeah, it's not bad, right? It's not bad. At least I don't think it's that bad, but some people do. If you're someone who wants to just memorize formulas, which I hope that you're not, because there is a formula for this. I'm very hesitant to give you this formula, but I'm going to give it to you anyways, just because some people like seeing things as formulas. This method of doing this can be generalized, right? This method can be generalized. So if I have here d dx of the integral, and let's say I have a function in the bottom, right? Let's call that g of x. And I have a function in the top, let's call that h of x, right? So if this was like x cubed and this up here was x squared, this still works, by the way. You could do it for if the x cubed is in the top or if it's in the bottom, right? Of some function f of t dt. This right here is going to be equal to, right? Again, if we just let little f be equal, the antiderivative of little f be equal to capital F of x, it will be equal to this. This is going to equal to d dx of capital F of h of x minus capital F of g of x. And when you take the derivative of this, we end up getting the chain rule, right? And when we chain rule this thing, we'll end up with the derivative of the inside function times the derivative of the outside function, which is just f of some stuff, minus, again, over here, derivative of the inside times the derivative of the outside, which is just f of some stuff. But the stuff that goes in there is what changes, right? The stuff that was in here was h of x, so the stuff that's in here is this h of x. The stuff that's in here is g of x, so the stuff that's in here is g of x. I know that looks like a bunch of nonsense, mumbo gumbo nonsense, right? But here it is right here. If this right here is your function, this is f of t, right, is equal to inverse tangent of t. This right here is f of h of x, because h of x is that x cubed. All I did was just took the inverse tangent and I plugged in x cubed. Over here, that's the derivative of that h of x. That x cubed derivative is 3x squared. So again, I don't like memorizing formulas, especially formulas that look this messy. If I just remember the concept, it makes it a little bit easier to deal with these problems. And that's how I like to do it. I like to go up here and just straight up go from here down to here using the fundamental theorem of calculus. But if you want to use formulas, this is the formula that will do it for you, and we'll actually have you guys solve it. I was supposed to have you guys have some homework up, but instead we would use this formula if both intervals values were functions. Yeah. This idea also applies if it has it up here as well, but I'm just letting you know that this thing can work for, you know what, let's do one real quick. Let's do one real quick. And again, I don't like using that formula, but you can if you want to. So here, let me show you real quick one last problem before we call it a day. So let's say I was asked here to find the derivative with respect to x, right, of the integral. Let's go with this one right here. This one looks fun. X squared to x plus x squared of the square root of t times tangent of t dt. I'm going to go close my door real quick. All right, dog. Didn't even want to come in here. All right. Sorry. So, again, I like the idea of just doing the chain rule, and then it's basically, if you know about integrals, right? We subtract the top from the bottom. So I don't bother memorizing this formula, but you can if you want to. But this is what goes through my mind, right? If I take the derivative of the integral, I end up back at my function, right? So the first function I have here is the square root of some stuff times tangent of some stuff, right? And the first stuff I'm going to be dealing with, let's do this in blue, is this one right here. It's going to be x plus x squared x plus x squared. And then don't forget to do the chain rule, which is to multiply this whole thing with the derivative of what's inside of x plus x squared, which is 1 plus 2x. The fundamental theorem of calculus tells us I'm supposed to subtract this, right, from the same function evaluated at x squared, which is going to be, since I take the derivative of it, end up back at the same place. It's going to be the square root of some stuff times tangent of some stuff. Well, what's that stuff down here? That stuff is going to be x squared. And what's inside here? That's also x squared. What do I multiply this by? The derivative of that x squared, which is 2x. And that is my answer. Ta-da! It looks horribly messy, but it's the answer. You've taken the integral and the derivative, and that's what you get. Again, I don't memorize this thing. I just worked it out like that, like how I said it. I use the second part of the fundamental theorem of calculus, which is the idea that if you do the integral from a to b of f of x dx, that's just equal to capital F of b minus capital F of a. And then if I were to do the derivative of that, right, this would go backwards, right, and end up back at just f of b minus f of a. Anyways, that's the idea here. That's how, I don't know, does that make sense how I worked through that? Hopefully it did. If not, I'm going to put up some homework problems for you guys to practice this and try this out for yourself. But that's it. This is your answer. It's the function, right, that you're dealing with, the square root of t, tangent of t, bam, bam, evaluated at these points, subtracting, of course, because, you know, fundamental theorem of calculus subtracts the b minus a. And then don't forget to chain rule what your b and what your a is. And you're done. Because, like I said, the derivative and the integral are inverses of each other. They're inverse operations. They cancel each other out. But the only thing is you just have to be careful when you do that derivative part that you include the derivative of the inside function, the a and the b, the chain rule. Don't forget to chain rule. All right, I'm a little bit behind on putting up your homework. I just realized this while I was going through your stuff. For your homework, you're going to have 2 assignments up. I'll set them on 2 different dates. You don't have to do them both at the same time, but you, yeah, one of them is going to have the average value theorem applied, and the other one is going to have the fundamental theorem of calculus applied. Yeah, I believe part 2 though. I think I'm going to have you guys practice this more rather than this, but that should be on there. Other than that though, guys, that's it for today. Hopefully this wasn't too crazy or too confusing. And if it was, please let me know. Again, I can't tell if you guys are okay or not. But let me know before it gets out of hand. Okay? Stop by my office hours. I will be in my office hours today from 1 to 2, as well as the rest of the week. But yeah, keep an eye out for your homework assignments. Like I said, I'm going to put one up for the average value theorem, and I'm going to put one up for the fundamental theorem of calculus. All right? And then that's it. I'll see you guys on Thursday, and we'll wrap it up there. All right. Have a good rest of your day, guys. Bye, everybody. So long. Have a great day. You too. See you.